Today's topic is on point-slope form for the equation of a line. Point-slope form in any textbook that you look in is going to appear this way. Y minus the y value of a point equals the slope times x minus the x value of a point. I've placed arrows next to the things that we would end up replacing with values. So the m value would get replaced with whatever slope you have, and the x sub 1, y sub 1 would get replaced with whatever point you know your line's passing through. The form that I have written down here is just a variation of it, and this form down here is what's also referred to as function form. And so in every function that we deal with from this point on, quadratics, exponentials, anything else, we're going to talk about a shifted function form, where your point that you know on the graph, this time instead of calling it x sub 1, y sub 1, we're referring to it as hk. So that's our point of origin. And then the stretch for a line is called the slope, but in all other functions we're going to call it a stretch. That stretch is the value a here, which would be the same as our slope in an equation. So you may see me refer to this a couple times throughout because it sometimes makes more sense to talk about it this way. So let's just do a quick recap of what you already know with slope-intercept form. When we write an equation in slope-intercept form, you're just taking the slope times x and adding the y-intercept. The reason why this works is because the slope times x, if I took my line and I was going through the origin, the point 0, 0, then every y value on this graph is simply that slope times the x value of where I'm at. Here's why this works. When you calculate the slope and you're taking the rise over the run, in this case I would take a run of 2 and a rise of 1, and I call my slope 1/2, we oftentimes think of this as a rise of 1 for a run of 2. But if we divide that out so that we have a unit rate, or in other words, when the denominator is 1, for every 1 unit of run, I'm going to rise exactly 1/2. So this just says every time you take one step over on the x-axis, you need to go up a half a step. Over a step, up a half a step. So if I'm going to go over 6 steps, then I'm going to need to go up 6 sets of a half, or a half times 6. That's slope times the x value, because I'm starting at the origin. If I want to go out to an x value of 100, then I would take 100 sets of a half, or a half times 100. That's what the a times x is right here. It's telling me whatever amount of rise you have for each unit run, multiply it by the amount of run that you went. Now that's going to get me all the points on this line, but this line is exactly, in this picture, 3 units below the line I really want to have. So once I've done y equals 1/2 times x, I need to take all those points and I need to add 3 units to them so that they become 3 larger, or 3 higher on the y-axis. And that will then calculate for me all those y values on my graph. So that's why slope-intercept works. It's all based upon an idea of steps out from the origin times that unit rate, and then add to it the height that you started at, or the height we need to go up to get that line. Notice when we're doing our cup activity that we did, we could go through and figure out that our unit rate here was 1 inch per 2 cups, or in other words, 1 inch per 2 cups is the same as a 1/2 inch for every 1 cup. And that was our unit rate. And we saw right here that when I added 10 cups, or this looks like it's probably 8 cups, that it added 8 times a half, or 4 inches. So that's what we were just talking about back there. Now, if I start with a point that that isn't on the y-axis, and I know my slope, that's going to allow me to actually get another point if I want to, I could extend this line back and see where it crosses the y-axis. My graph right now is not drawn all the way to the y-axis, and so the question is, how do I find the y-axis? Well, essentially every point on this line that I pick, x, y, is going to have a couple things here. I know that however many steps I had to take to get to that x value, so this x to this x, that difference, x minus 4, is going to be multiplied by my slope to get the change in the y value. So multiply that by my slope, and that's going to be the difference of my two y values, y minus 8. So this change, 4, x minus 4, times my slope gets me this change. And this change here is my y minus 8. So that's the relationship between these two pieces. Notice this comes back to our definition of slope. If I take the rise there, y minus 8, and divide it by the run, x minus 4, that's going to give me my slope of this line. It should equal 3 halves. So that's where this is coming from. Notice if I divide both sides of this by the x minus 4 in parentheses, that's going to get me that slope formula again. It's just a proportion. This chunk over that chunk equals my 1 unit rise over run. So onto our equation. Like I set up here, if I take my slope, 3 halves, and I multiply it by the change in the x values, x minus the point I started at, that should equal the change in my y values, y minus the y I started at. This is point slope form. If you think back to what I showed you on that first page, it said slope times x minus x sub 1 equals y minus y sub 1. Here, I'll show you right now. Y minus y sub 1 equals slope times x minus x sub 1. So that's our point slope form. Now, how does this help us get the equation of the line in slope intercept form? Well, essentially, I'm just solving for y now, and we've done this multiple times. The first thing I would do is eliminate the parentheses by using my distributive property. So 3 halves x minus, and then 4 times 3 halves is 12 halves, or 6, equals y minus 8. And because I'm solving for y, I'm going to now add 8 to both sides, and I get 3 halves x, I knew that part, that was my slope, plus 2 equals y. We can check this, because I have a picture here, I can check this actually by extending that line back, still going through my 2 points. So it passes through this point here, and that point here continues to have a slope of down 3 over 2, and you can see that in fact that is where it's crossing the y-axis. Another way I can check it is, if it's the right equation, it has to have the right slope, 3 halves, and it has to work with the point that's on that line, and that point that I was given was 4, 8. So I can check by putting 4 in for x and 8 in for y, and it should work. 3 halves times 4 plus 2 has to equal 8. So if we go through and check this, 3 halves times 4 is going to give me 12 halves, or 6, and 6 plus 2 equals 8. So that's point slope form up here, and we transformed that in 2 steps into slope intercept form. Let's try another one. This particular one, we aren't given the y-intercept. We can kind of see it, and maybe it looks like it's going through the y-axis here at, what is this, 6? And it looks like it might be going through, or maybe a hair above. If it was going through at 6, though, that would mean that over 2 up 1 is my slope. And over 2 up 1, notice, does not keep me on that line. So that can't be the y-intercept. It actually has to be a little bit higher than that for me to stay on this line. So I'm going to use the 2 points that I have, and the first thing I'm going to do is find my slope. Remember, that's what this coefficient here is my slope, and oftentimes referred to as m. So my slope for this line, 7 minus 5, that's the difference of my y values here, over 1 minus negative 2, leaves me with a slope of 2 over 3. And I can check it on my picture here, up 2 over 3, that makes sense. So thinking about it in terms of a unit rate, it means that every time I go over 1 unit, I'm going to go up 2/3. Over 1 unit, I went up 2/3 again. Over 1 unit, I went up 2/3 again, and I'm back on that integer values. So logically, this thing must be 4/3 higher than it was here, or 1 1/3. So this has to be a height of 6 1/3. But rather than calculating them with a graph, because sometimes your x values might be hundreds of units away from the origin, so rather than calculating it that way, we're going to use this idea of steps. So starting at this point, and going to any other point on the line, no matter where it is. Call it x, y. We're trying to define the equation of this line. First thing I'm going to do is figure out how far have I gone on my x's. What is x minus the x I started with? Use either point. I'm going to use this one. So that's the one I circled over here. X minus the x that I started at, that's the change in my x values. That change in x values times by my slope has to equal the height that I've changed, so the change in the y values. My change in y values here was y minus, remember I have to go same order, so I started with the x, so I'm going to start with the y minus, in this case, 5. The only thing I have to do to simplify this is change this to plus or positive. Now somebody else might have looked at this and said, but I want to use this point because there's no negatives in it. Could I use that point? Would I get the same thing? Absolutely. I'm still looking at the same concept. From this point now, my change in x values times by the slope should give me my change in y values. So I'm going to say that my change in x values, x minus 1, times by the slope, 2/3, has to equal my change in y values, y minus 7. Either one of these describes the same line, and we know that because if we go through and change them both into slope-intercept form, we'll end up with the exact same answer. So let's do this. 2/3 times x plus 4/3. Remember the 4/3 I talked about? We're going over 2 steps and up 2/3 twice, that's 4/3. That has to equal the change in my y values, y minus 5. Now I'm going to add 5 to both sides, and that's because I was already starting at a height of 5, so whatever height I just went up, I have to add that to the height I already am to get the y-intercept. So now I get 2/3 x plus 5 plus 4/3. 4/3 is just 1 1/3, so 5 plus 1 1/3 is 6 1/3 equals my y value. If I tried it with the blue equation, it would do the same thing. Notice in order to do it with the blue one, I would get a 2/3 x minus 2/3. Well, I'm subtracting 2/3 because I have to go backwards a step to get to the y-axis. Equals y minus 7. And then I'm going to add 7 to both sides. Here again, I'm doing this because I just figured out how much it's going to go down. It's going to go down 2/3, but I'm starting at a height of 7. So when I do this, I get 2/3 x plus 6 1/3 equals y. It's the same slope-intercept equation. When we change it to slope-intercept form, ours should all look the same because we have the same slope and we have the same y-intercept. But point-slope form can look different from person to person depending which point you used on that line. Do you feel like you're starting to get the hang of this? Why don't you try a few here? I've got 3 lines here described. We've got the first one is going to go through the point 8, 0. Be careful, this is not a y-intercept. This is a point on the x-axis. So it goes through the point 8, 0 with a slope of 3/4. This one goes through the point 11, 8 with a slope of 4/3. And my last one, I've simply given you 2 points. I haven't given you a slope. So I want you to start by putting it in point-slope form and then change it to that function form or slope-intercept form, the one that says y equals. So pause the video right now, and when you come back, I'll have worked out solutions for you. Okay, I'm back. I hope you tried these on your own. I'm going to go through the explanation on each one. Notice the first 2 are actually ready to put into point-slope form. I'm going to remind you the idea behind point-slope form is from any point x on the line to the point that you're given, in this case 8, in this case 11, and in this case we've got 2 options, so I'm going to hold off on that one. That amount of change along your x-axis times your slope, and remember your slope is how much rise for every unit run, that amount of change in run times your slope should give you the amount of change in rise. So it should give you y minus 0 here, and this should give you y minus 8. And then I can take that point-slope form and I can go to slope-intercept from it if I want to. This last one, I need to first find the slope, and the slope here I can find by taking the change in the y values, 14 minus 4, so going from the second point to the first, has to be put over, or as a fraction over, the change in the x values. And so I end up with a 10 over negative 15 or negative 2/3 as my slope. So I actually have two options here. For any point on the line xy, I know the difference of the x to the point that I started with. Let's say I use this point. That difference of x times by my slope has to equal the difference of the y's. So from that point y to this y's value. There's one point slope form equation. The other option, if I were to use the other point, is to say the difference of my x's goes from x to the negative 9, so x minus negative 9, which becomes plus. That change in x times the slope has to equal the change in y minus 14. So on the next few pages here, I'm just going to show you real quickly how I went through and got them slope-intercept form. Each one done the same way, starting with your point slope form. You would then distribute through the parentheses. And after you've distributed, if there's a constant over here that you need to get rid of, you'd add its opposite to get rid of it. In this case, the constant was 0 already. Notice you can check your equation. The slope has to match what you were given, and it does. And then the point that you were given, in this case the point 80, needs to work when I plug it in for x and y. Second problem started with this point slope form. I distributed the 4/3 into both. Now some people get a little panicky when they're starting to multiply a fraction by a whole number. Use your calculator. You can write it as a mixed number if you'd like, because this is going to be a value on the y-axis. So you can convert this, and then I need to add my 8 to both sides in order to get that y value alone. And so now when I add the 8 to the negative 14 2/3, I get that y-intercept. And again, I can go ahead and check this. I know my slope matches, and my point 11,4, if I plug in 11 for the x and 4 for the y, it should work out. And it in fact does. I changed my mixed number back into an improper fraction because I don't have a calculator on me, and then I just subtracted them and got 24/3. Finally, our last one, from either point slope form, you'll notice that the process is the same and the result is the same, even though the two starting points looked different. So I distribute into the parentheses, and then I isolate the y. Over here, I distribute into the parentheses, and then I isolate by adding 14. Both of them get me the same thing. In order to check one of these where you weren't given the slope, you don't want to see if the slope matches because you might have messed that up. Always go back to your original information. My original information was 2 points. So I want to make sure that my slope-intercept equation works for each of those 2 points. So I'm replacing the x with 6 and the y with 4 and checking that. And then I'm going back and replacing the x with negative 9 and the y with 14 and checking that. So hopefully you feel like you've got a pretty good handle on this. Practice some more in class. Come ask questions if you're